Hello everyone, and welcome back to another remote sensing lecture video. In this video, I want to sort of go through, on a conceptual level, the difference between a spectral response curve, which again, it covers all wavelengths in a given region, and is explicitly talking about reflectance, to the idea of a spectral profile, which is the bands along the x-axis, and the y-axis is whatever the pixel value means, and it may not necessarily be percent reflectance. It could be some other thing. But anyway, what I want to do really quickly is talk conceptually about what this looks like to go from a spectral response curve to a spectral profile in terms of what happens to the information. And this is going to make a lot more sense as we go through it. So what I've done over here on the right-hand side, we have a typical spectral response curve that we've seen up to this point. On the left-hand side, I have the first 7 bands of Landsat. I have the band number, the color that they represent broadly, and then over here, this is the wavelength range. This is the region of the spectrum that the band is sensitive to. So band 1 is going to be sensitive to anything between 430 nanometers and 450 nanometers. Hopefully that makes sense. This is nothing new. So what I want to do is I want to just take a second and talk about what this means relative to creating a spectral profile. So what will happen here, right? So we'll take band 1 as an example. So basically what is going to happen is in here, right, to convert from a spectral profile, to convert from a spectral response curve to a spectral profile, what's going to end up happening here is that band 1 is going to look at this. It's going to say, okay, I'm sensitive to everything from 430 nanometers to 450 nanometers. Right, so there's 200 nanometers, sorry, 20 nanometers in here. There's 20 nanometers in here. 20. Actually, let's go down, right? This right here, this is 20 nanometers. Right, there's 20 wavelengths in here that this is sensitive to. And what we've done is we collapse that down to a single point, right? A single pixel value. So the 20 different nanometer values, right? All this information gets collapsed down to a single point. This is also sort of the idea when we talked about the spectral dimension of remote sensing, and we talked about spectral resolution. Right? This is the same sort of thing that happens when you go from hyperspectral to multispectral. Right? You collapse the wavelengths down into fewer and fewer numbers, right? So we have 20 different values here in the spectral response curve being collapsed down into 1 for the being collapsed down into 1. So I'm going to put a dot in the middle. This is kind of hard to do given the size of the graph, but we're going to go through an example here in a minute that's going to make it a little more clear. So we can do the same thing with band 2, right? So it goes from 450 nanometers. Right, so we're going to have that line is going to trace that line too because they're right next to each other, all the way up to 510 nanometers. So that's going to be like roughly right there. Right, so that's going to get collapsed down onto a single point. Right, so all the values, right, all of these values in this range are going to be averaged essentially. It's a little more complicated than that, but essentially they're going to be averaged to give you one value that represents the entirety of this blue range here. Green is going to do the same thing. All right, so green is going to go from 530 nanometers, which is going to be roughly, again, I'm sort of doing this freehand, right? It's going to be roughly right there, to 590 nanometers, which is going to be roughly right there. Right, so all those wavelengths are going to be averaged down to a single point. Right. I'm going to do one more. I'm going to do red. Right, so red is 640, 670, so that's going to be roughly right there, right, to roughly right there. And again, all those wavelengths are getting averaged down to a single point. So you can imagine we could go through the process and do all the rest of these. But what we've done here is we've taken what would in effect be thousands of wavelengths of individual data points, and we've consolidated them down into 7 points. Hopefully that makes sense. What I want to do now is I want to transition over to an Excel spreadsheet that actually walks through in a graphic way what happens as we consolidate from a spectral response curve, which covers every wavelength across the entire region, into these discrete packets that are represented by bands in an image. Okay, so let's go ahead and open up an Excel spreadsheet. Okay, so this image right here, this is the spectral response curve that we were just dealing with, right? If I switch back over here, right, you'll see it's the same thing. I've just graphed it in Excel. And so each one of these points, right, each one of these dots, this is a wavelength. And you can see that we go from, again, roughly 450-ish up to roughly 2,500-ish. So this is what it actually looks like when you graph out a spectral response curve. And the reason this is a spectral response curve is because we have information at virtually every wavelength. And this is sort of the best data that we could get. So this is a spectral response curve. What happens when we start to decrease the number of bands, right? We go away from that every nanometer. What happens is we decrease that. So let's go to something like Sentinel data. So Sentinel-2. Let's go to Avarice. So Avarice is 150 spectral channels. So we go from several thousand down to 150. Right. You'll see here that we're still retaining the same basic shape, but you'll see that in some regions, maybe some regions more so than others, you'll see these points are starting to separate out, right? And that's because we're not measuring every nanometer, right? We're measuring a range of nanometers, and I've gone ahead and I've put the dot in the center wavelength. So this dot is the center wavelength for that band, but it's actually measuring a couple of wavelengths on either side. So let's go ahead and compare the two together. So the blue line is going to be our original data, right, the best data that we could come up with, and the orange line is going to be our 150 band hyperspectral image. And you can see here we haven't really lost any information, and that's good, right? That's a good thing that we still have the same shape. Okay. Well, let's see what happens. Let me turn those off for a second. When we decrease it down to what would be a traditional multispectral sensor. Right, now we really start to see that change in shape. Right, you have a lot less detail. The distance between the points is a lot bigger. Again, all I've done is I've taken the middle wavelength that the band is sensitive to, and that's the wavelength that I've used so that I could plot these this way. But you can see that the shape has started to change. Let's go ahead and put our data back up here. Okay. Right. So in this case, right, the blue, this is our original spectral response curve. And now this gray line here, right, this is our spectral profile from a multispectral image that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that has 13 bands, right? So we've went from thousands of wavelengths being measured individually to 13 bands that are measuring a chunk of the spectrum. And you can see that we still have the same general shape. We still have the same general shape, especially in these shorter wavelengths, right? The visible still looks kind of the same. The near infrared looks very similar. But then when we get into the shortwave infrared, right, we've got these big swaths, right? Large gaps between the dots. And you can see that we're losing all of this unique shape and unique features are all being lost. So let's take it a step further. Let's turn these off. What happens if we go down to something like Landsat, which is the one that I always like to pick on? it has 7 bands. So we go from the 13 that we have right now down to 7. What happens? Well, we've lost this shape here, we've lost all these shapes here, we've lost all those shapes there. So you can see as you decrease the number of bands, right, as you go from a spectral response curve where each wavelength is being measured to a spectral profile where now you're talking about bands that cover some region of varying widths and varying numbers of bands, you can see how that affects sort of what your overall shape of the curve looks like, and it affects what you can do with it. So just to sort of hammer this point home, let's go ahead and let's turn off that just so you can see the full effect. Right. So we went from this nice sweeping, every nanometer is being measured, we get all these features, especially in the shortwave infrared, that are just gone now, right? We failed to capture those because of the way that we've set up our sensor and the spectral profile that is generated as a result. So again, hopefully this makes a little more clear the difference between a spectral profile and a spectral response curve, and hopefully it highlights the importance of that spectral resolution that we talked about before as well. So we're kind of tying in multiple points here. If any of this doesn't make sense, I strongly encourage you to reach out. Thank you.